All right, so we finished with 12b, and we kind of got this. This is what I call the sneaky one, right? The sneaky place where the derivative doesn't exist, because so far I've been saying it has to be connected how? Smoothly, right? And if you look at the graph of x to the 1/3 or the cube root of x, it is very smooth at the origin, right? But it's still not differentiable there because we have a vertical tangent, right? Now there's going to be another way to determine where a function is differentiable. All you have to do is find the domain of the derivative. But we need to have the derivative function in our hand, and we don't have this one, and I'm not going to do it using the limit definition, all right? So be on the lookout for vertical tangents. If you don't have the equation, a lot of times they'll give you a graph, and something looks like it goes vertical. It's very hard to tell just from a graph if the slope is infinity or just like 5,672,721.78. It's really hard to tell the difference between those numbers. So it'll usually say in the question, the graph of f of x has a vertical tangent at. And you're like, oh, okay. So what looks like it's a vertical tangent is in fact a vertical tangent. All right, so here's your next parent function, x to the 2/3, because remember this one is x to the 1/3, another version of it. X to the 2/3 is the same thing as the cube root of x squared. And so this graph, all we have to do to get it is to take the other graph and square all the y values, which is going to make it a little bit steeper, and all the negative values are going to become positive. So this one looks like this, and it comes in like that, vertically, and then it goes out vertically. So it's an even function. It has y-axis symmetry. And I know you recognize this function because in little school, you used to always draw like seascapes, like that. And then you would maybe put like a shark in here, right? And no seascape was complete without the sun in the upper corner, right? Like that. And you either did your rays like long, short, or some of y'all did like curvy rays, remember that? And the sun was always cool, wasn't he? He was a cool sun. Not cool like in temperature because he was really hot. But yeah, the sun always wore sunglasses. That's how you know it was a cool sun. And then no graph was complete for the seascape without a couple of these birds, right? So I call this your bird graph. That's what it looks like. It looks like those seabirds. But if you notice the tangent lines, let me see if I can do that again. If you drew a tangent line here, and I lassoed it so I can move it, as you surf the curve, it's a negative slope right there. And as you come in towards 0, what's the slope approaching? Negative infinity, right? Vertical. And then it bounces out and becomes positive slopes. So there's the surfboard. So the real reason why this derivative doesn't exist is because there's a vertical tangent line still, but it's also because the slopes aren't going towards each other. On one hand, they're approaching negative infinity, which is a negative number, and on the other hand, they're approaching positive infinity. So there's your little tangent line surfboard. So anyway, this one is also noticeable because it has that cuspy look right there. All right, so here's a cusp at x equals 0. And at every other place, the function is going to be differentiable. So even though this function is continuous at 0, it's not differentiable at 0. All right, and this one's pretty obvious. In fact, your seascape here is full of cusps, right? The waves make cusps. The shark fin at the top is cuspy. So non-differentiable all over the place. All right, and then you've got functions like this. Let's look at 10 minus x. We've seen this one already. If you plug in a 10, you get 0. So the function's defined at 0. If you wanted to sketch this one, let's put it in the standard transformation form. It would look like that. And that takes your radical dude function, which comes out of the origin. The negative on the inside is going to reflect it across the which axis? If it's in front of your x's are switching, so that's a y-axis reflection, and then the minus 10 moves it to the right. So this guy actually looks something like this. Actually, let me do it a little bit different. It comes out, remember, vertically, and then it does that. So this is one of those ones that has the smaller domain also. The function is defined at 10, but the derivative is not defined at 10. We have another vertical tangent right there. Vertical tangent line. And so f would not be differentiable at 10. Would it be differentiable at 11, though? No, that doesn't even make sense, right? The function doesn't exist there. So that would be obvious. So this one is differentiable everywhere strictly to the left of 10, but it's continuous for less than or equal to 10, okay? So really, the visuals that we have for non-differentiable are sharp turns / cusps, and then the sneaky one that is actually smoothly connected, vertical tangents, okay? So here's a very important theorem. It says if f is differentiable, that is if the derivative exists at that point, at x equals c, then f is continuous. So we can write that like that. D, this arrow in this case doesn't mean approaching, it means implies. So big D is differentiable, big C is continuous. So differentiability implies continuity. If a function is differentiable, then it will be continuous. So in geometry, I think, you studied statements, logical statements. So you have the statement here, which I'll just rewrite, D implies C. There was something called the converse. If you remember the converse of the statement, what that does is it flips the if-then. The if is really on this side, the then is over here. So if a function is continuous, or differentiable, then it's continuous. The converse flips them around, and it would say then if a function is continuous, it's differentiable. Is that true? No, that's not necessarily true. We have lots of examples. There's an example where the function is continuous but not differentiable. So that one's not true. We draw a line through the implies. Then you have the inverse. The inverse statement keeps the if-then the same, but it negates them. And so using logical symbols, that looks like this. The not symbol is either that little bar like this, that means not, or sometimes you'll see like a little tilde. It depends. I use the, the half of the right angle there. So is that true? That says if it's not differentiable, then it's not continuous. Is that true? No. And another counterexample is that one. There's one that's not differentiable, but yet it's still continuous. So if you have a statement, the converse and the inverse aren't necessarily true. But then there's this last one called the contrapositive, and it combines the converse and the inverse. It negates the flipped order. So that would say if it's not continuous, then it is not differentiable. Is that one true? That one's true. Okay, so for every statement, the contrapositive is always true. Negate the flipped order. And this gives us a whole new category then of places where functions are not differentiable. Not just sharp turns, but any discontinuity. So at any cusp, at any jump, at any hole, at any vertical asymptote, and maybe the occasional oscillation discontinuity, the function is not going to be differentiable. Okay? Now, the only type of statements for which all four of those are true are if and only if statements. And we've had some of those. Those are definitions. Okay? But for a regular statement, just the statement and the contrapositive are true. So that's what this says. The contrapositive of the very important theorem, if f is not continuous at C, then it's not differentiable. So not C implies not D. Super important. Okay? If it is differentiable, we know it's going to be continuous. But since continuity is a prerequisite, if it's not continuous, it ain't going to be differentiable. Okay, so here's what we're going to be doing in the future. We're going to be checking for differentiability using the shortcut rule, okay, instead of using the alternate form. But remember, it takes more than just the slopes being the same for a function to be differentiable. It must first be what? Continuous, okay? So let's go ahead and look at example 13. It's a simple piecewise function. And it's the line 2x minus 1 to the left of negative 1 and out negative 1. And it's the line 2x plus 1 to the right of negative 1. So let's go ahead and use the alternate form one more time and check for differentiability. Remember, the alternate form checks both. It checks for continuity and it checks the slopes all at the same time. So let's go ahead and set it up from the left-hand side. We'll take the limit as x goes to negative 1 from the left. And remember, we're doing f of x minus f of negative 1 all over x minus negative 1, which is x plus 1. So that would be the general form. Let's go ahead and plug in now. F of x from the left, this is where you choose the piece that's defining the function on that particular side. Which piece is that from the left of negative 1, top or bottom? top, all right? So that's going to be 2x minus 1. Here's how it checks for continuity. It uses the same y value from both sides because the y value is only defined by one of them. And that's going to be, in this case, the top one because there's an equal sign. So if I plug a negative 1 in, I get negative 2 minus 1, that's negative 3. So I get minus negative 3 all over x plus 1. So that gives you 2x plus 4, which when you plug in it gives you 2x plus 2, sorry. Which when you plug in a negative 1 does give you 0 over 0. So if I simplify this, I get 2x plus 4. If I factor out the 2x plus 2, sorry, I could factor out the 2 and get 2 times x plus 1 over x plus 1. Those divide out, and I get 2. Now, not surprisingly, the slope is 2 coming in from the left. Could we have discerned that without doing much work, just by the way it's defined? Yeah, it's a line mx plus b. And so m is 2, the constant slope of 2. So it's 2 coming in everywhere from the left. And because it was defined there, we got that slope. So now let's do it from the other side. The limit as x goes to negative 1 from the right-hand side is, again, f of x minus f of negative 1 all over x minus negative 1, which is x plus 1. So this part changes every time. The variable piece, f of x, changes depending on which piece you're using. So now from the right side of negative 1, it's going to be the function 2x plus 1 minus f of negative 1 is still using the top piece. And that's going to be negative 3 still, all over x plus 1. So that's how it takes care of continuity. Let me simplify that one. That's going to be 2x plus 4 all over x plus 1. And if I use direct substitution now, what do we get? 4 minus 2 is 2 over 0. Is that indeterminate? No, that's some type of infinity, so it's dne. Right? So what? Is the function differentiable at negative 1? No, they have to both be finite and they have to both be the same. And I'll just say, how about this? Since 2 does not equal dne, that's kind of silly. But one of them exists and the other one doesn't. Comma, f is not differentiable at x equals negative 1. So the alternate form takes care of matching the slopes up because we're using the difference quotient and using the same function value on both of them. Make sure it's continuous. All right. So here's how we're going to do it in the future. We're not going to use alternate form. Once we learn the shortcut rules in 2.3, if we ever want to know if a function is differentiable for a piecewise function, we're going to do it the following way, right? In order to be differentiable, it must first be what? Continuous. So let's go ahead and check that first then, using the continuity argument. We'll take the limit as x goes to negative 1 from the left, this time of the function, not of the difference quotient. And I'm not going to go ahead and write the piece in there, but we know how to do that. That's going to be negative 2 minus 1. We get negative 3, which happens to also equal f of negative 1. Now, let me do it this way. F of negative 1 is also negative 3. So again, the limit from the left is equal to the function value. The road coming in is attached to the bridge. The limit as x goes to negative 1 on the right-hand side of f. That's the bottom piece. You plug in, you get negative 2 plus 1 is negative 1. So is f even continuous there? No. So here's your argument. F is not continuous at x equals negative 1, comma, since negative 3 does not equal negative 1, comma, and therefore, and so, f is not differentiable at x equals negative 1. You can't just go straight to negative 3 doesn't equal negative 1, therefore f is not differentiable. You have to link the chain reaction in the right order. Okay, it's first not continuous there for this reason, and now that it's not continuous, boom, that implies that it's not differentiable. Now, had it been continuous there, What we would then do is we would find a piecewise derivative using the shortcut rules. A piecewise f prime, much like we did up here on example 7. And once we would get our piecewise derivative, then we would just analyze the slopes from the left and the right. And if the slopes were the same, now we know it's continuous and the slopes are the same, it's going to be differentiable. And if the slopes weren't the same from both sides, now it's only continuous but not differentiable, okay? So that's how we're going to do it in the future. But the alternate form takes care of both of them at the same time. Okay, that's pretty much it for this section. I just want to show you one more thing, and it's related to your calculator, okay? There's one other form of the derivative that is worth mentioning. There are probably other forms as well. This one's called the symmetric form. And like the modified form and the alternate form, it gives you a numeric value, okay? Here's what it looks like. It says, let's say you have a function f of x, and let's say you're trying to find the function value right here at x equals c, okay? What we've been doing is we've just been plugging another value over here that is h units away. So that's going to be c plus h. And then we let the distance between those go to 0, right? And so the secant line goes to the tangent line, and essentially we have one fixed point. But what the symmetric version does is it then goes h units on the other side and picks another point called c minus h. And what it does is instead of using the point we want and the other point we have to use, it finds the slope of the secant line between those 2 points that are symmetrically spaced on either side of the one we want. Now what happens as h goes to 0? These 2 points here start to get closer and closer to the point we want, and so we still get a secant line that approaches the tangent line. It just does it by a slightly different method. So here's what the setup would look like. F prime of c is equal to the change in the y's, f of c plus h minus f of c minus h, all over 2h now, because the distance is h plus h. Now, you don't ever have to evaluate anything that way, but it's significant because this is how your calculator is programmed to find derivatives. I just showed you that your calculator can find a derivative value for you, dy dx. Your calculator is using this right here, all right? So let me show you how to do it on your calculator. Let's go ahead and use your calculator. This is a segue into tomorrow's. The function is 3 minus 6 times x plus 1. Now, before we start, let's figure out the x-coordinate of the vertex. Remember to do that real quickly without putting in the standard transformation form is you take your argument and you set it equal to 0. So that means x equals -1. And notice it's a transformation of the absolute value function. So what should the value of the derivative be at -1? Well, let's go ahead and sketch it. This is the same as -6 times x plus 1 absolute value plus 3. The negative reflects it across the x-axis. The 6 makes it steeper. And then we're moving it left 1 and up 3. So here's what it looks like. There's the vertex. It's opening downward. What would be the slope everywhere to the left of -1? Very good. This number out in front, plus or minus, is your slope. Since it's increasing now to the left, it should be 6 everywhere to the left. It should be -6 everywhere to the right. And again, what should the derivative be at -1? dne, right? So let's go ahead and answer these without a calculator. What should f prime of -2 be? Well, that's to the left of the vertex, so it should be +6. F prime of 0 is to the right of the vertex. It should be -6. And then f prime of -1, where the vertex is, should be dne. Should be. Well, let's see if your calculator knows that. Now, instead of doing it from the graphing screen like I showed you, here's what we are going to do. Let's go ahead and plug that function into y1. 3 minus 6, absolute values. I still like to go math number 1. Math number 1. And then x plus 1. So now instead of sketching the graph and going to your trace or second trace, your calculate menu, let's go to the home screen because there's another way to do it. If you hit your alpha window, this is your shortcut. Look what number 3 says. It says n deriv. If you choose that, it shows up like this. Now, we don't know what this is really, but I'll walk you through it. This is going to be your independent variable x, so type in an x there. As soon as you type in x, you get this little x over here. We're going to recall the function from y1, so that's alpha trace that unlocks your y's, and select 1. Now, this vertical bar is the when bar, it's the evaluation bar. It means evaluate the derivative of this with respect to x when x equals, and let's go ahead and plug in a -2. This does the same thing as if we were to graph it and find the slope graphically, but we don't need the graph. You hit enter, and it gives you +6. Is that what we were expecting? Yep. All right, let's do it again. Second enter recalls it. So now let's come over here and change -2 to 0, which we should get a -6 out now. And hey, we do. Your calculator is pretty smart. Well done. Well, now let's do it again, but let's do it at the vertex, which is at -1. Your calculator should give you an error or DNE or something like that, right? But instead it gives you 0. Is that right? 0? If that were a parabola opening downward, the tangent line would be what? 0. But it should be DNE here because 6 doesn't equal -6. So why is your calculator telling you it's 0, which is obviously wrong? It's because it's programmed using the symmetric quotient. So if you want the slope at -1, it's choosing a point over here to the left and a point over there to the right. Now, because this function has symmetry through its vertex, it's going to calculate the slope of that secant line, which should be what? 0, right? And then it's going to choose another point that's closer and the same distance on the other side, and it's going to calculate that secant slope, which is still 0. And it does that all the way up until it gets painfully close to values on either side of -1 and 1. But because of the symmetry, that secant line is always going to have a slope of what? 0. So, ergo, your calculator takes the limit of all of those numbers, 0, 0, 0, 0, 0, as those 2 points get closer together, and it infers incorrectly then that the slope at the vertex is in fact 0, when we know for a fact that it is not. So your calculator is only a tool that helps you crunch numbers. Does it do any of the thinking for you? No, you're the boss of the calculator. Now, does it have some pretty good jokes? F prime of -1 equals 0. Ha, LOL, whatever y'all say these days. Yeah, that's funny, calculator. I didn't know you had a sense of humor, but I like it, okay? So make sure that you're always doing the thinking for the calculator and not the other way around. You are the boss of your calculator, okay? So act like you are. All right, that's it. Your test is pretty much going to be through here. Tomorrow we're going to kind of do a little bit more with the calculator, but it's just to kind of do another day. We'll also review what's going to be on the test tomorrow as well. Your calculator will not be used on the test, even though tomorrow's lesson is only with the calculator. It's just a good time to do it, all right? So come with any questions you have tomorrow. Make sure you're doing the worksheets. Make sure you're looking at the practice tests. Your test will be essentially 1.1 through 2.1. So basically anything from the last test is still fair game. All right, we done.